2025 A-Level Combined Mathematics, Paper 1, Part A, Question 1. This question is regarding mathematical induction. It says, using the principle of mathematical induction, prove that 9 times 2 to the power of n is less than n plus 3 factorial for all n elements of the positive integers. To do this, using mathematical induction, we first need to establish a base case. For the set of positive integers which goes 1, 2, 3 and so on, the best base case is n equals 1. So we're going to try that. We're going to try n equals 1 at the start. So let's say over here at the very top left, try n equals 1. So now trying n equals 1, this inequality has two sides, the left hand side and the right hand side. The left hand side, or LHS, is equal to 9 times 2 to the power of n, or 9 times 2 to the power of 1, which is 9 times 2, which is 18. On the other side, on the right hand side, we have n plus 3 factorial, which is 1 plus 3 factorial, which is 4 factorial, which is 4 times 3 times 2 times 1, which is 24. So we have the left hand side and right hand side, and we can clearly see that 24 is bigger than 18. Therefore, the right hand side is bigger than left hand side. In our inequality, we expect the right hand side to be bigger than the left hand side. So in this case, since we have that property that the left hand side is smaller than the right hand side, this is true for n equals 1, meaning that what we are trying to prove for works for n equals 1, or our base case. Now that we have the base case established, what we need to do next is to assume that it's true for some value, well, let's say n equals p, and then prove for the next value n equals p plus 1. So we're going to go down here and we're going to write that we're going to assume true for a particular value n equals p, where p is an element of the set that we want. In this case, we want the positive integers, so therefore we need this p to be an element of the positive integers. So we're going to assume true for p such that we're going to say for p such that this inequality is true. Therefore we're going to assume that 9 times 2 to the n, where n equals p, or 9 times 2 to the p, is less than n plus 3, where n is p, so p plus 3 factorial. So we're going to assume that this is true. I'm going to write this as equation 1, and we're going to be using this equation later. So this inequality is known to us, and now assuming that it's known to us, we're going to try for the next value of n, which is n equals p plus 1. So we're going to do here, we're going to go down here and say consider the next value of n, which is n equals p plus 1. So for n equals p plus 1, we again have an LHS and an RHS. The LHS is, in this case, is going to be the LHS when you substitute n equals p plus 1, which is going to be 9 times 2 to the power of p plus 1. So that's going to be 9 times 2 to the power of p plus 1. Now I'm going to do a little clever thing here. I'm going to take this 2 to the power of p plus 1 and split it into a 2 to the power of p times a 2 to the power of 1, which is going to be 2 times 2 to the power of p. The reason why I'm doing that is because we can relate this 2 to the 9 times 2 to the power of p to this bit here, and the 2 will remain separate. So I'm going to split that out and say that this is 2 times 9 times 2 to the power of p. Now similarly, if we consider the RHS is n plus 3 factorial when n is p plus 1. The RHS, which I'm going to write down here, RHS, is equal to n plus 3, or p plus 1 plus 3 factorial, which is p plus 4 factorial, which I'm going to write as p plus 4 times p plus 3 factorial. We can of course do this since the factorial function is just the product of all the positive integers from your starting value down until 1. So due to this, p plus 4 factorial is p plus 4 times p plus 3 times p plus 2 times p plus 1 times p, and so on downward, which is the same thing as p plus 4 times p plus 3 factorial. Now that we've done this, what we're going to do is make the observation that this 9 times 2 to the p, which is there in this left hand side, is also there in our original inequality. Similarly, the p plus 3 factorial, which is there on the right hand side's equation, is also there in our original inequality. Now here we can see that this original inequality part, 9 times 2 to the power of p, is multiplied by another value 2. And similarly, this p plus 3 factorial is multiplied by another value p plus 4. Now, since p is an element of the positive integers, or we could say since p is an element of the positive integers, we know that p is greater than 0, which then follows that p plus 4 is greater than 0. Now, p plus 4 is greater than 0, comma, p plus 4 is also greater than 2. So p plus 4 is positive and it is also greater than 2, because p is greater than 0. So we can derive these two facts using the fact that p is greater than 0 since p is an element of the positive integers. So now that we've done that, make the observation that since p plus 4 is greater than 2, and previously from 1 we discovered that 9 times 2 to the power of p is less than p plus 3 factorial, over here with the left hand side and right hand side's products, the left hand side is a product of two numbers here, where this number 2 is smaller than this p plus 4, and this number 9 times 2 to the power of p is smaller than this number p plus 3 factorial. And more importantly, both of these are positive and both of these are positive. So due to that, we have the product of two positive numbers which are smaller than two other positive numbers that are also being multiplied together. So due to this, we can say that the product of the two smaller numbers is smaller than the product of the two bigger numbers. So here, since we know this, which I'm going to call 2, from 1 and 2, since we are multiplying two smaller numbers together to get this number here, that number is going to be smaller than the two bigger numbers p plus 4 and p plus 3 factorial from here being multiplied together. So from these two, we can infer that the left hand side here and the right hand side here, if you compare them, 2 times 9 times 2 to the power of p, which is this part, is definitely smaller than this bit here, which is p plus 4 times p plus 3 factorial. Now that was the condition that we wanted to show. We wanted to show that given that it's true for n equals p, it would be true for the next value n equals p plus 1. And we have just shown that it's true for n equals p plus 1 by the fact that this form is exactly what we get if we substitute n equals p plus 1 into this inequality here. And we can see it is true. This left hand side here is in fact less than the right hand side. So now that we've done that, we can write down here right below it that it is true for n equals p plus 1. Now this would usually be enough. However, we are generally expected to write a formal sentence that summarizes this proof by mathematical induction. So in this formal sentence, we are expected to write the starting bit, which is the base case, and then we are expected to write that we assumed a certain thing, and when we assumed that, we were able to prove for the next value of n. So we are going to say we assume for p, and then we are able to prove that it's true for n equals p plus 1. The general structure of this sentence is like this. We first say, hence, by the principle of mathematical induction, which is the part that we always say, mathematical induction, and then we describe what we did. So what we did first was establish the base case for n equals 1. So we're going to say, since it was proven for n equals 1, and then what we did was assume it true for n equals p. So we're going to say, and when assumed true for that value n equals p, it was proven true for the next value n equals p plus 1. So we're going to say was proven for n equals p plus 1, and at this point, now that we have all of these conditions where it was assumed true for n equals p, proven true for n equals p plus 1, and we have a base case of n equals 1. If it's true for n equals 1, it will be true for n equals 1 plus 1 or n equals 2. If it's true for 2, it will be true for 3. If it's true for 3, it will be true for 4, and therefore it is going to be true for the entire set of positive integers of n that we are expecting. So at this point, we're going to stop it here and say the above, and the above, we don't really need to rewrite this whole thing again. We can just say the above is true for all the values of n that we are interested in, which in the question is all n which are elements of the positive integers. So we can say down here it's true for all n element of the positive integers, and we can close out our final answer. So that's going to be our final answer. It's going to be broken down into these steps, where first we establish the base case, then we assume true for a certain value n equals p, then using that we check for the next value and show that it's true for the next value as well, and finally we write out this closing statement, this closing sentence that confirms the fact that the mathematical induction works in this case, and we can prove that it's true for all n elements of the positive integers. Finally, let's take a look at the distribution of marks for this kind of answer. So first off, for the base case bit, this bit right here, where you try for the base case and prove that it's true for the base case, you get 5 marks. And then after that proving for the base case, when you then go to assuming true for a certain n equals p, where p is an element of the set that we're looking for, in this case the set of positive integers, you get 5 marks. It is important to note that you need to include the fact that this number that you're looking for is an element of the set that you're interested in this case the positive integers. Afterwards, when you consider the next value p plus 1, writing down the first bit here gains 5 marks. And then after that, when you start substituting the previous assumption in and finally get to the result that proves that it's true for n equals p plus 1, you get another 5 marks. It's not just for this line, of course, it's for all of the stuff before that line leading up to that line. And finally, for writing down this final statement that ties the base case and the assumption and the final result together, you get another 5 marks. So for all of this whole sentence, you get another 5 marks, giving you a total of 25 marks for this question. Thank you for watching. If you have any feedback, post them in the comments down below, and goodbye.